Yeah, please, Daniel.
Okay. Should I just go ahead?
Oh yeah, please. Yeah, sorry, I don't really do a very formal introduction.
I
usually.
didn't expect it. It's fine.
Yeah, it's okay.
So I wasn't quite sure how to do the talk. But I was sort of prompted off Jeff's choosing a title for me, which was great because I didn't give him a title, which was about supergravity equations and generalized geometry. So I thought what I would do is tell you kind of about supergravity and in what sense I think it might give you. So I'm going to talk a reasonable amount about supergravity, actually, as sort of background. So if that's not helpful, I can move more quickly into other things, but maybe we see how we go and you tell me if that's a good way to do it. And please interrupt me if things aren't making sense at all. So I'm going to tell you a bit about supergravity and equations. And generalized geometry. And here's the idea. So the general idea is that I'm going to tell you that supergravity is a machine. There's some supergravity machine. And it spits out interesting, so sort of nice differential equations. So things which have nice descriptions using moment maps, or maybe ideas of stability, and that have nice finite moduli spaces, finite dimensional moduli spaces. And the way it arranges things is that it naturally arranges things. So it sort of naturally arranges the geometry in terms of generalized geometry or extensions thereof. So maybe also exceptional generalized geometry, which is just some further generalized geometry where you think about more complicated generalized tangent spaces. And what it does is it sort of gives generalizations of a whole load of sort of any geometry you could think of. So sort of the Hermitian-Yang-Mills equations, Calabi-Yau manifolds, G2 manifolds, Sasaki-Einstein spaces, etc. So my idea was to tell you a little bit about in what sense, what this machine is and how it spits out these things. And the point is that there's quite a lot of dials you can turn on the supergravity machine. And depending what dials you turn, you get out different kinds of differential equations, which generalize different things. So the one I'm going to focus on is the one that generalizes the notion of Hermitian-Yang-Mills and Calabi-Yau. So that's the Hull-Strominger system, which I think probably Mario has talked a bit about already. And Roberto was going to talk about, except it got postponed. Did I get that right?
I think that's about right. Yeah.
Yeah. So, so I guess my first question, if this is a good thing to do, maybe I'll start and you can stop me or ask me questions as we go along. Is that sound
absolutely?
Good?
Yeah. No, it's 100%. Yeah.
Okay. Good. All right. So the first thing I'm going to do is just tell you about. So the basic point is going to be that we're going to see that supergravity and geometry get related. Geometry is inherent in supergravity in two different ways. So I'm going to tell you the two different ways it appears in supergravity. And then I'm going to tell you a way in which actually we can put those two ways together. And putting those two ways together is kind of what gives us this nice picture of these differential equations. So I want to start by telling you about, so I'm going to tell you about supergravity and geometry, part one. So what is supergravity? So I'll say sugra for supergravity. So what do you have? So we just take some d-dimensional spin manifold, M, and let's have some spinor bundle on it, S. And it's going to turn out that if you wanted to look at the details, you're interested in sort of real Clifford modules. But I'm not going to do any details. Let's just say there's some spinor bundle sitting there. And the supergravity is built out of the things in the supergravity are physical fields, what I would call a field. And they come in two types. There are bosonic ones. And those are things that just correspond to just tensors on the manifold. And it always includes, because we're doing supergravity, it always includes a metric. So we'll always have some metric, which is some, okay, just to be pedantic, I'll write it as some section of symmetric tensors. And then it'll have, in general, a whole load of other stuff, which are just other tensors, functions, forms, different things. And then it has some fermionic degrees of freedom. And they're basically things that are tensors, tensor, some spinor bundle. Mostly they're just spinors, actually. So there's one thing which you see, which is living in some non-trivial tensor, tensor a spinor bundle. And there'll always be, because it's supergravity, there'll be some gravitinos. So there may be more than one. And they're going to be some objects which live in sections of T star M times the spinor bundle. And there might be several of them. So I'm labeling them by some index, and that will go up to some integer n. And this is the n of the supergravity. So sometimes you see people talking about supergravity in d dimensions with n equal 1, n equal 2, n equal 4. That refers to this number of gravitinos. And then the theory, so those are the objects in the theory. And then there's some action. Which describes the dynamics. And that always has some, so there's some volume form defined by the metric. It always has some Ricci scalar for the gravity. And then it has a whole lot of other stuff, which tell you about the dynamics of the other fields here. So these other bosonic fields and the other fermionic fields. So I should say that the fermions, there's always gravitinos, but again, there's other stuff in general. And then the key property is that this theory has a supersymmetry, which is an infinitesimal variation of the symmetry. So infinitesimally, you can transform all the fields. So for example, the gravitinos always have a term that looks like some derivative of some spinor parameter plus some other stuff. This is the Levi-Civita derivative, or the spin connection corresponding to the Levi-Civita derivative. And then the other fields, the metric will have some variation, and all the other fields will have some variations. And they're parameterized by some set of spinors, which are sections of the spinor bundle. And again, there are n of them. So under these infinitesimal transformations, this action is invariant. So the equations of motion have that as a symmetry. And that's the supergravity. The point is that these requiring this symmetry is very restrictive, or it can be very restrictive. So there's symmetry, so the supersymmetry. So the supersymmetry restricts the form of the action. And for example, if we were in 11 dimensions and we just had one supersymmetry, so one gravitino, the theory is unique. There's only one theory you can write down with certain combinations of bosonic and fermionic fields, and the action is completely determined. Similarly, if you were in 10 dimensions and you had n equal 2, there's actually two cases. You can do A or B. There's two variants which have two supersymmetries. That's to do with the fact that there are two spinor representations because it's not even dimensions. Again, the theory is unique. If you're in 10 dimensions and if you have n equal 1, it's almost unique. In fact, I'll talk about that theory and we'll see to what degree it's almost unique. So in general, you can define a number. So let's call it the number of supercharges. Let's call it n, which is just going to be the real dimension of the spinor bundle times the number of supersymmetries. So it counts the total number of degrees of freedom in the supersymmetry transformations. And this is always going to be, it turns out this is always some power of 2, and it's less than or equal to 32. If you go above 32, you have to have a theory which has fields which have spin higher than 2, higher than the graviton, and we don't know how to write down any interacting theories like that. And the answer is that the smaller n is, the less constrained the theory is. So all the theories which have n equal 30, little n equals 32 are unique. You have no freedom. If n is 16, that's like this case, in fact, it's pretty unique. You have a little bit of freedom. And then as you keep going down, you get more and more freedom in the kinds of theories you can write down. Am I making sense? Anyone have other questions?
I guess you'll get into this to the almost and almost unique.
I will. I'll give you a bit more. Yeah. So what I want to do first, what I'm going to do first is tell you about actually what was the first supergravity that people looked at, essentially. So let's do the example of
Can you say more about this? Sorry.
Yep.
The supercharges. Can you go back to what are the supercharges? What do they live?
So all I'm doing is counting the number of degrees of freedom in the supersymmetry parameters epsilon. Okay. So they're sections of some spinor bundle. So if I have one of them, the number of, I take the dimension of the spinor bundle and then I multiply it by however many epsilons I have. Maybe that wasn't, did I misunderstand?
Yeah, I just wanted to know what do you mean by supercharges. It's just the,
so it's sort
the
of
dimension of the.
Yeah, so if you count the total number of degrees of freedom in the spinor parameters, that's this little n.
Okay, thanks.
Yeah, no, that's good. So let's do the simplest case. Let's do well, not the simplest, but the sort of standard case. Let's do 4 dimensions n equal 1. So this has actually the spinor bundle here is a 4-dimensional real bundle, or a 2-dimensional complex bundle, depending how you want to think about it. But it's so n is 4 here. So this is a lot smaller than these completely determined theories where n was 32. So what do you have? So it turns out that the fields come in multiplets. And all the multiplet is some that corresponds to some irreducible representation of super Poincare algebra. So if you looked at not some curved manifold, but flat space, we're in the case where we're interested in a Lorentzian signature because we're doing physics, we've got a time direction. And the symmetry of flat space is the Poincare group, translations and rotations and Lorentz transformations. That actually can be extended into a supergroup. And there are corresponding supersymmetry transformations. So it turns out that a way to think about the field content of the supergravity is actually just in terms of those irreducible representations of that group. So, and there are essentially, there's more than this, but there are essentially three possibilities that one's interested in that appear in the supergravity. So the first one is the gravity multiplet. So this is just a useful way of organizing things, these multiplets. So that has in it the metric and a single graviton. And again, we're in signature 3.1 because I want to do we're doing physics, got a time direction. There's another multiplet which is called the chiral multiplet. And that has in it, well, it has a complex scalar field and it has a fermion. So actually, I'm going to imagine that we have several of them. So let's put some index here. So I'm going to have some I that runs from 1 up to some integer, which I'm going to call dz for reasons that will become apparent. So these are complex scalars. And these are some, these are sections of the spinor bundle. So we could have several, so a single multiplet would have a single complex scalar and a single fermion and lambda. And in general, we can have several of them. So we'll have several of them. And then the other thing you get is you get what's called a vector multiplet. And that has some gauge field or some connection and some fermion. So this is some connection for some principal G bundle. And this is some spinor valued in the Lie algebra.
Sorry, can you say how many Chiral multiplets you have? Is D subset? What is this number?
Sorry, say again? Oh, this D subset, I can choose. So one of the freedoms with n equal 1, thank you, sorry, I didn't say very well. One of the freedoms in n equal 1 is you can have any number of chiral multiplets.
Okay.
So in this theory, in the maximal D equals 11 theories, there's only one multiplet, it's a gravity multiplet. You're stuck with it, it's got a fixed action. With these theories where little n is smaller, you always have a gravity multiplet, but you can have additional things and they'll fall into other multiplets. And in general, you can have as many of them as you want if you're just doing the classical theory. If you're doing the quantum theory, then it gets more complicated. But for the classical theory, so here I can have any number of chiral multiplets, and I can have actually any number of vector multiplets, but they'll always arrange themselves into some connection for some, there's some connection for some group G. So here's the first way that the geometry appears. So this is the geometry part 1. It turns out that these chiral multiplets are not really just, they're not really just functions. So really, you should think of the chiral multiplets as some map from the manifold, the 4-dimensional manifold, to some other space. So really, they're just complex coordinates on this space Z. And what is Z? Well, Z is some dz dimensional Kähler-Hodge manifold. So it's got some symplectic, the symplectic form, I'll call it pi, has to live in the integer cohomology. Sorry, too many Zs. Or equivalently, we can think of it as the first Chern class for some line bundle.
Dan, sorry, when you say that chi is a spinor valued in the Lie algebra, you mean in the adjoint bundle? Or
in the adjoint bundle, yeah. Yeah.
Oh, okay.
Yeah, good. Yeah.
Thanks.
Yeah, thank you. So yeah, I don't know what I should write. Add P or something. I don't know what I should write. Yeah. So the supersymmetry tells you that these chiral multiplets, the way they arrange themselves, actually are not just a set of functions, but more generally they're maps into some Kähler manifold. So we see geometry appearing in the sense that these things, there's geometry appearing here. And there's a corresponding action. So there's an action which looks like, so again, it's got some Ricci scalar. And then it has, so I'll write it in components, but it's really just the pullback of the metric on the Kähler manifold. It's got some kinetic term for the field strength for the gauge fields in this multiplet. Strictly speaking, there's a little more freedom here. This can multiply by a function, but I'm just going to ignore that. And then it has a potential term. So it's got some term which is just some function of the scalar fields. It's not holomorphic. Depends on both so it's some function. This V is some function on the Kähler manifold. And then it's got all the fermions. Yeah.
Is this is the form of this action fixed entirely just by supersymmetry?
Yes.
Okay.
So let me tell you how. So supersymmetry tells you that this has to be the pullback of a Kähler metric. So this is like the kinetic term for the scalar fields. It has to be the pullback. And it also tells you the form of this potential. So let me tell you the form of that potential. So this potential has to be written in the following form. So again, I'm going to write it with components. So it's some derivatives of some other function. Plus the square of a moment map. Okay, so what are the ingredients here? So first of all, there's this W. This is really a section of the line bundle squared. So remember because we've got a Kähler-Hodge manifold, there's some line bundle that's telling us about the symplectic form. This thing is some meromorphic function on that. And this is what's called the superpotential. And so this object here, this derivative here is just the fact that this is the section of a line bundle. I need a little connection on it, which I inherit from the Kähler metric. So this is really just this is the connection on here that you get from the Kähler metric. And then the other object that appears here is this mu, which is a moment map for the holomorphic isometries on Z. So we think of this as a G action. So we have this gauge group G, either the whole of G or some subgroup of it acts as a holomorphic isometry on the Kähler space. And these mu's are just the moment maps for that action. And this is the square of the moment maps using some suitable metric on the algebra.
Sorry, can I interrupt? K is pi from the previous slide, is it right? Like K is your distinguished symplectic form.
Oh, sorry.
target.
Yeah, I guess I'm calling it, when it's the metric, I'm calling it K.
Oh.
And when it's the, yeah, sorry.
Okay,
sorry.
no, that's fine.
Perfect.
I understand.
Yep.
I understand.
Yep. So the supergravity, this n equal 1 supergravity, is determined by choosing some z, choosing some superpotential on z, and choosing some g action. And those three ingredients will completely determine the form of the supergravity. So there's quite a lot of freedom. You can have as many, you could have any Kähler-Hodge manifold you want. You can choose your groups and so on. So there's quite a lot of freedom there. But once you've chosen those, you can choose the superpotential. But there's still, it's much more restricted than a general theory with some complex scalars and some gauge fields would be.
Sorry, can I ask two things? So
Please.
FG is the curvature of the gauge field, right?
Yeah, exactly.
And the DI, DJ bar, this is the Chern connection for a Hermitian metric on L2 square.
Sorry, so again, these guys?
Yeah, this is the covariant derivative acting on the section for
Yes.
For a. Okay. So
this is take the line bundle that's defining the symplectic form, then the Kähler metric will define a connection on that line bundle, and that's what this is. Yeah, I'm not sure if I'm using the right words, but that's the. Okay, now, one thing you can do is you can look in this theory for a particular class of solutions. So you can look at what are called supersymmetric Minkowski backgrounds. So what do I mean by that? So I want to consider the case where G is just flat space. So it's just the flat metric. So I'm going to take the...
I have another question. So what does it mean W to be meromorphic? What it measures the singularities of the...
That's a good question. I was going to say it was holomorphic, and then I thought that it can actually have singularities, but now I think about it, I'm not quite sure what to say. So maybe I shouldn't have said that. I should think of some examples. Let me come back to let me be Boris Johnson and say I'm not going to get an answer. Yeah, I mean, the usual physics examples, you actually just choose the Minkowski space to be flat space. Sorry, the Kähler space to be flat. And then you definitely allow superpotentials, which can be, for example, have poles. So you just choose Cn, and your superpotential could look like 1 on phi. That'd be perfectly allowed. So I don't know what more to say than that. So these supersymmetric and Minkowski backgrounds, we want to take phi to be a constant, G to be flat, and we're going to take the gauge fields to be 0. So we just take, we'll take F to be 0. And we'll also take all the fermions to be 0. And then we require that there exists some section of the spinor bundle such that all the variations vanish. So this is called, these things are called the killing spinor equations. But they're kind of boring in this case because I'm choosing the metric to be completely flat and I'm turning off almost everything. So really, these are just going to be the solution here is going to be some constant spinor, constant with respect to the flat connection. And all we have to worry about is what values can we choose for these things so that all the variations vanish. And it turns out that these conditions are equivalent to two things. So first of all, you need to set the W function to 0, and you also need to make it extremize it. So this, you know, I'm taking the D with respect to the phi fields. And these are what physicists would call F-term equations. And then the other thing you need to do is you need to set the moment maps to 0. And those are what physicists would call D-terms. And if you look back at the potential that we wrote down, you see that this term's gone, this term's gone, these terms are gone. So the potential is 0. So these conditions imply that V is 0. You can have solutions of V equals 0 which don't satisfy these things, but if you have this supersymmetric condition, it will imply that V is 0. And it will also imply actually that dV is 0. It's a minimum. So, but these two conditions give you a nice picture of what the moduli space of solutions is going to look like. Because we start with some Kähler manifold Z, and then the F terms are some holomorphic conditions, or meromorphic, what am I saying? I'll say holomorphic. So we're picking out some subspace inside here, which will also be Kähler because it's some holomorphic conditions. So that's some complex submanifold. And then the D terms, well, the D terms just take a symplectic quotient or a Kähler quotient. So they just take you some moduli space, which is this thing, the symplectic quotient by G. Or equivalently, if we want to think of it in the stability picture, we can think of this there being some, you know, in general, some polystable points, and we mod out by the complexification of G. So that's sort of this, that's if we had some stability.
Sorry, when you say that Killing spinor equations are equivalent to these F term and D term equations, this is not automatic, right? One has to argue something.
Yeah, you have to work through some stuff. So you have to, I haven't shown you how, you have to look at these equations. It's not too bad, actually. What happens is that if you remember, I told you there were these fermions here in the chiral multiplets and fermions in the vectors. And all the variations of the bosonic fields will be 0 because they depend on the fermionic fields, and we turned off all the fermionic fields. So when you do supersymmetry, the variation of the bosons depends on the fermions, and the variations of the fermions depends on the bosons. So this background, we're turning off the fermions, so all the variations of the bosonic fields will be 0. The variation of the gravitino will be 0 because it's we're looking at constant spinors. And so you get the variation of this fermion and this fermion. And if you just go, if you look at the form of the supergravity, so when people write down supergravity, it writes down all the variations as well, you find that the variation of this one is proportional to the superpotential, is proportional to derivatives of the superpotential, and this one is proportional to the moment maps. So it's not too bad, but yeah, you have to go through the details.
Is G the gauge group, or is the group of isometries of Z?
So it's really, strictly speaking, it's the subgroup that acts on the gauge group that acts as isometries. The ones we've gauged, the ones we've chosen. You can choose whether you gauge certain isometries or not. So you just choose some G action. And for me, I'm not really distinguishing. So you could have some larger group here that's larger than the group that acts on the Kähler space, but I'm just going to take them to be the same. But the you'll only get D terms for the parts of, obviously for the ones that have moment maps, so for the ones that are acting on the group. And you don't have to act with the full isometries. You can act with some subgroup if you want. So it's your choice. And in this case, the Kähler potential, which you can think of here as some section of the line bundle, is the norm functional. It's the norm function for the stability. So you can think, so another way to say that is that setting the moment maps to 0 is equivalent to extremizing the Kähler potential. So this is the Kähler potential under the imaginary group action. So if we're complexifying the group, we just take the imaginary part of that. The real part will leave the Kähler potential invariant. So the basic thing I want to take away is that there's some geometry appearing in the sense that there's this Kähler space. And furthermore, if we're interested in these supersymmetric backgrounds, we have a nice geometrical picture for how the moduli space of those backgrounds is going to appear. And it's got these two things. One, it's got some holomorphic condition. And then secondly, it's got this D term, which is just a symplectic quotient. Now you can do this whole story for other space-time dimensions and other n. And when you do that, you get all sorts of, this leads you to different multiplets and different geometries. So whereas here the chiral multiplets were had to live in this Kähler manifold. So in general, you can get all sorts of other things. You can get things called special Kähler manifolds. Special real, very special real. I'm just saying that because who came up with the name? Quaternionic Kähler. And so on. So there are other geometries you get if you were to do this in 5 dimensions with n equal 1, or 6 dimensions with n equal 1, or 5 dimensions with n equal 2, and so on. And in each case, the supersymmetric backgrounds, so the supersymmetric Minkowski backgrounds, correspond to other geometrical, so some other geometrical gadget. So for example, if you were to take the case where the multiplet naturally described a map from space-time into a quaternionic Kähler manifold, you would get the supersymmetric background would give you some quaternionic Kähler quotient. Quaternionic Kähler, the cone over a quaternionic Kähler manifold is hyperkähler. So this is really just a hyperkähler quotient. So all I'm trying to get at is that you can get other geometries and you can get other kinds of gadgets that are appearing when you start looking at the dimension of the Minkowski background. Okay, am I doing okay? Is that making sense?
Actually, I wonder if I could just back up a second.
Yeah.
Can you just say a bit more about this top line, about the moment map vanishing? You say it's extremizing the Kähler potential. How exactly? Or
yeah, so I'm now going to get into the stability picture that I'm no expert on. But if I understand, if we're in the case where we've got a Kähler manifold, so long as it's the Kähler quotient is equivalent to modding out by some complex action if we've got some stable point. And for that, you have this norm functional. And you usually have some picture where there's so we're living, this is the fiber, the L fiber, and there's some functional on the L fiber, and it's concave with respect to the, so you get some shape like that. And as you move in the imaginary, so I'm moving around in this imaginary action, and it's moving me around here. And if I can argue that it has a minimum, then that minimum is the point where the moment map equals 0. So, and in this case, this function on here is nothing other than the Kähler potential. So it follows directly from writing the Kähler potential. If you write, you know, your symplectic form as you just write it in the usual form, and then you have some group action, and you then go from here to the moment map. You can show that having the moment map equal to 0 is equivalent to extremizing something here, just by kind of taking off the derivatives. Not sure I said that very well, but
no, okay, thank you. Yeah.
I think all I'm really trying to say is that this puts it, because this is a Kähler quotient, it puts it already into this picture where you can think about stability. Okay, so if that's all right, I was now going to go on to the second way to get geometry out of supergravity. And then we'll see how to connect the two of them. So let's go to the other extreme. Let's look at this 10-dimensional n=1 theory. So in that case, we have the dimension of, the real dimension of this thing is 16. So n is 16. So it's almost the maximal one, but not quite. So what you then get is you get two types of multiplet. You get a gravity multiplet. And this has a metric. It has a scalar field, which is called the dilaton. And it has a two form. Sorry. Which is the B field. And then it also has some fermions, so it has the gravitino. And then it also has another field, which is just some section of the spinor bundle, which is called the dilatino. But the point is, this is the supergravity that starts having the degrees of freedom that you see in generalized geometry. But it turns out, I said there was some freedom here, so it's not completely determined. You can also have some vector multiplets. So again, actually, you get some connection and some gaugino, which is some section of the adjoint bundle tensor the spinors. So if there was no freedom to have any extra, if these weren't there, then you'd only have the gravity multiplet and everything would be determined. But we now actually have a choice of also adding some vector multiplets. And so we now get a theory. So that's the freedom. We can have as many, we can choose vector multiplets in some gauge group, whatever we want. And there's an action. And the action looks like some e⁻² phi. Then there's some Ricci curvature. There's some kinetic term for the dilaton. Then there's something which involves this H field, which is the derivative of B roughly. And then there's some curvature term, and then there's some fermions. And the thing that appears here, this H, locally, I write it as dB, and then to this I have to add, one has to add some Chern-Simons term. So the supersymmetry is clever enough to tell you that you have to add this term. If you don't add this term in, you won't get a supersymmetric theory. And so in this case, you see that DH is going to look like C of F wedge F, where this is sort of the first Pontryagin. This is some representative of the first Pontryagin class. So we need that this must be 0 because this is exact. So you can.
Then
yeah.
Why does the B field doesn't have a supersymmetric partner?
Why does the
B field doesn't have a B field inno?
Good. It just turns out that they don't line up exactly like that. So the nomenclature is not very good. It's not really that the dilatino is only associated to dilaton. You get the whole package. Bad notation. Yeah.
I mean, I wonder, can you say a bit more about how this ansatz for H is implied by supersymmetry? It's somehow just dug out of these variational equations. I mean,
yeah, so it's really hard to write down supersymmetric actions. And the way people did it originally was that you build it up order by order. So you start with you tailor expand in the fields, and things get determined at each order. So it just turns out you just have to have this term. Now I'm trying to think if there's an easy way to tell you why. I don't think I can think of a, yeah. You just have to do some hard work.
through these killing spinner equations, I guess. Somehow this pops
Yeah, so
out.
you want to write down some explicit variations of everything. And you need to find what those variations are so that the action is invariant. And it just turns out to be very restrictive.
Okay.
Yeah, I mean, there's a sense in which these theories are kind of magical, right? I mean, if you the way we're writing this, it seems a bit arbitrary, right? Why this dilaton, why this two-form B field, why that term, et cetera, et cetera. One of the points later on is that actually you can repackage this whole story in terms of generalized geometry. And from that point of view, everything looks more natural. It really just looks like a theory of a theory of a generalized metric. Some Riemannian, some theory of some curve. Just this whole thing just becomes some generalized Ricci tensor scalar. And from that point of view, this Chern-Simons term is appearing because you're looking at some transitive Courant algebroid, and these are the gauge fields that are allowed in that, and that Courant algebroid naturally has to have this kind of twisting in it. So I don't know if that helps.
Yeah.
So from this point of view, this Bianchi identity is something classical, because from the string theory point of view, this is this anomaly cancellation condition. But from this point of view, it's just classical.
Exactly. So here I'm just talking about the supergravity. When you go on and do string theory will always give you a supergravity theory as a low energy description, but it doesn't give you a general one, it gives you a particular one. And so in that case, in supergravity, you get a particular, the gauge group has to be of a particular type. And as you go to higher, as you know, if you go to higher order terms, you get contributions from space-time curvatures. Yeah. So So you see that this theory is almost completely determined. The only freedom you have really is just in choosing what your gauge group is. Everything else beyond that's determined. Okay, so now again, we can, so where does the geometry come in? So now again, we can look at what's called a supersymmetric compactification. So say, for example, we really want to do 4-dimensional physics because we were in 10 dimensions. So let's assume, I'll go put some subscripts on. So let's assume our 10-dimensional manifold now is some flat Minkowski in 4 dimensions times some compact internal space. So on here we have some compact manifold. And we've got non-trivial metric B field dilaton gauge connection. But we'll set all the spinors to 0. All the fermions, sorry. So this is a bit like the case we did before, but the case before we didn't have any internal space. We only had this part of the space. So on here, I'm just putting a flat Minkowski metric. I'm having 0 on here. We have no B field, no dilaton. So all the action here, all the interesting fields are going to be turned on the internal part of the space. And from a physics point of view, we want to imagine that this is quite small, so that effectively the universe we see is effectively 4-dimensional. That's why it's called compactification. So you can also think about the spinor bundle, and the spinor bundle is going to decompose into some tensor product of a spinor bundle in 4 dimensions and a spinor bundle in 6 dimensions. And so if we take a section, we can write it as some 4-dimensional spinor tensor some internal 6-dimensional spinor. And then again, we can look for solutions to the variation of the fields being 0. So again, we're going to look at the killing spinor equations. But now they're more complicated because we have some non-trivial fields on this part of the space. So we need to take some general spinor like that and look to see when do the variations of the fields vanish. So if we took B equals phi equals A equals 0, so we just had geometry, then these variations being 0 turns out to be equivalent to saying that the Levi-Civita, the spin connection derivative of this internal spinor has to be 0. So we decompose the spinor into external, internal. We look at these variations. You do some unpacking, and you find that they end up telling you that the spinor on the internal part has to be covariantly constant. And so that's just on M6.
This is only assuming that B equals phi equals to, I mean, if all the fields.
Yeah, if we turn off all the other things. We turn off B, phi, and A, yeah.
So in general, the supersymmetry variations are less constrained.
Yeah, so we'll come to that in a second. Brilliant. So, but that, you know, so if we said this has a single solution, then that tells us that M is a Calabi-Yau manifold. Right, it's in general, this implies special holonomy. And in particular, if it was Calabi-Yau, you'd have a single solution to that equation. And that's really just coming from, well, yeah, okay. So what if so what if phi be
just
non-zero? Yeah.
One question about the previous slide. So these ansatz of the fields being only dependent on the internal manifold.
Yeah.
This is just an ansatz. It doesn't follow from supersymmetry or anything. It's really the ansatz of
purely a choice. Yeah, purely a choice. So you could look for, I mean, more, yeah, absolutely, it's good. So for example, you could look for other Minkowski spaces like 2-1 or 1-1, or you could even just ask, what about if I look at the whole thing and I just require some supersymmetry, what do I get? Yep. So what if they're non-zero? Then you find that the killing spinor equations become, so then the killing spinor equations become the following. So you find that now the spinor is covariantly constant, but now with some new connection, which is the Levi-Civita connection plus something that depends on H. So this is torsionful. And then you find that, okay, so these things are some Clifford actions. So H is a 3 form and phi is a 1 form. So I can think of them as acting by a Clifford action on the spinor. And those things have to vanish. And then similarly, if I take F as a 2 form acting on the spinor, that also has to vanish. So these are the equations you get. And they're coming essentially from, I told you the fields here were the fermionic fields were the Gravitino, the Dilatino, and the Gaugino. And for each of these, you get an equation, and that's essentially these 3 equations. This system is called the Hull-Strominger system. So if you have a solution of these equations, the set of equations is called the Hull-Strominger system. Now, epsilon is invariant under an SU3 subgroup of SU4, which is the same as spin 6. So I told you that the epsilon was a section of the spinor bundle on the internal space, which is 6-dimensional. Spin 6 is the same as SU4. So if I pick out one direction there, which is the solution to these equations, that's going to be invariant under some SU3 subgroup. So what that means is that, so that means this should be equivalent to some SU3 structure. So if I think of the metric and epsilon, that should be equivalent to some SU3 structure, which I can describe by some what would be a holomorphic 3 form if it was Calabi-Yau, and what would be a Kähler form. So if I have some SU3 structure, I get 2 invariant tensors. One of them is a complex 3 tensor, and the other one is some real 2 tensor. And they have some algebraic relations. So we should be able to repackage these equations into something on the structure. So in fact, you can. So Hull and Strominger did this. So you can repackage killing spinor equations as you get the e to the minus 2 phi omega is 0. So that tells you that it's still complex. However, it's no longer symplectic. So you get some e to the 2 phi omega, which omega is 0. You also get that if I act with the complex structure on D to get some DC, this is related to H. So it's not Kähler. And in general, for the gauge fields, you find that it's holomorphic and that so these look like the Hermitian-Yang-Mills equations, but for some symplectic form, which is no longer some two form, which is no longer symplectic. So this system of equations is also the Hall-Strominger system, just written in a different way. So this, if you like, is some natural string theory generalization or supergravity generalization of a Calabi-Yau threefold. Because if we just had a Calabi-Yau threefold, we would have just had the metric, but in the supergravity, you naturally have the H and the phi and the F as well. And if you just ask the more general question of when do you preserve supersymmetry, well, then you preserve this bigger set of equations. Now, you can note something else. So the Killing-Spinner equations imply the equations of motion. And these things are elliptic. The equations of motion are elliptic. So that would imply that we expect some finite dimensional moduli space. So because it's coming from the supergravity, we expect that this system should have some finite dimensional moduli space. So by thinking about these supersymmetric backgrounds, you get some, at least from a physics point of view, natural set of equations which generalize things that you already know. So more generally, so if you take, for example, d equals 11, n equal 1, or you take d equals 10, you take n equal 2a or 2b, these other theories, and you can take your 10 or 11 dimensional manifold to be some flat space in, I don't know, some p dimensions times some internal space. Then you get, these lead to other equations which generalize, say, G2 holonomy or hyperkähler, Sasaki-Einstein, etc. Sasaki-Einstein, you actually don't take this to be flat space, you take it to be some other symmetric space. But so again, there's a series, the machinery just spits out. So whereas the machine, when we thought about the one way we got geometry was that the supergravity had in itself, and it just, when you write down the action, it had some geometry. And depending on which dimension we were in, how many supersymmetries, we got different geometries. Similarly, when you think about these compactifications, depending where you start and depending by how big a manifold you compactify on, you get geometries which generalize things that you already know.
Can I ask something?
Yeah.
So when people study the G2 version of this Hall-Strominger equation, it's G2, heterotic G2 system.
Yeah.
They have a different ansatz for the three-form flux in 10 dimensions, right? In some cases they allow the three-form flux to be partially on the 4-dimensional space-time.
On the 3-dimensional space-time, yeah.
Yeah, and then you get, yeah, sorry, in the 3-dimensional, and then you get this tau zero torsion, yeah, non-vanishing, right? So in principle, can you do something similar for the 6-dimension?
Yeah, so roughly whenever you have some field which is the same degree form as the space-time you want to go down to, then you're always a sort of, then the physics would naturally allow you to turn on that form as well. So if I'm in 11-dimensional supergravity, there's a 4-form field strength. So if I compactify to 4 dimensions, I could imagine putting that 4-form on the 4-dimensional part of the space. And that will give you different equations.
But if I do from 10 to 4, can I allow the 3-form flux to have a, can I have a supersymmetric theory with some?
Yeah, then you would break the symmetry of the four-dimensional space.
Ah, okay, so it's not possible.
So you could do it, but then in a sense you're already going down to 3.
Oh, I see.
Yeah. It would be a special case of going down to 3.
And sorry to ask this other question, but
No,
is there an interpretation of the connection nabla in these supergravity terms, or not?
So I think the best interpretation of this guy, the nabla plus.
No. The other connection which appears in the Bianchi identity. What you typically take as
the R wedge R one, the nabla minus.
yeah.
Yeah. You can show that it won't be supersymmetric unless you choose that correct nabla minus. So again, it comes from supersymmetry by going to next order in curvature terms. So yeah.
What I mean is this part of the way you have presented things, this nabla connection in the tangent boundary is not present at all? Do you really need that to construct the supergravity theory in 10 dimensions, the compactification, or you don't need it?
Yes. So this you need in 10 dimensions. Is that your? I'm not sorry if I'm misunderstanding. That you need in 10 dimensions just to write down a supersymmetric theory. It will naturally actually appear in the variation of the gravitino. So it's already natural in the supergravity.
No, I mean the Bianchi identity. So you said that
the one in the Bianchi identity. So I wrote down a theory that had just a curvature term in it, but you could go to next order and write something like Ricci squared, or you could write Riemann squared, where this is the curvature of the metric. So I could ask, when I said the theory is unique, it's unique as a theory which has only 2 derivatives. All the equations of motion have only 2 derivatives in it. If you allow yourself to have equations of motion that have 4 derivatives in it, then there's more freedom. And so, for example, you could write down an action which started to have higher curvature invariance appearing in it. And if you want this to be supersymmetric, then you have to modify the Bianchi identity so that you see the other nabla. You see the connection, you see the curvature that corresponds to the other nabla.
Okay.
Maybe I'm misunderstanding, sorry.
No. The way you presented things is you said that supersymmetry imposes that the 3 form is D of the B field plus this Chern-Simons term.
Chern-Simons, yep.
Of the gauge field. But typically when you consider these series, you have also this other term coming from the Chern-Simons. It's Chern-Simons for the spin connection on the tangent boundary.
Yeah, so you'd have Chern-Simons of this minus Chern-Simons of the spin connection.
Yeah, and so my question is, does supersymmetry really impose that H is just the first 2 terms, and then or
so, good. So if you do supersymmetry and you restrict your action to only have the Einstein term in it, this term is not there. If you allow it to also have curvature squared terms in it and remain supersymmetric, then you have to add this term in. And it comes precisely with the minus, the other sign from the other one. So from a supergravity point of view, it just depends what order you're working at and how many derivatives you're allowing in the theory. So Jeff, if I keep going another 15 minutes or something, then I'll tell you how to connect these two bits of geometry.
That sounds great. Yeah.
Okay. Okay, so let's try and connecting 1 and 2. So 1, if you remember, was this idea that, say, the 4-dimensional theory, the scalar fields in the 4-dimensional theory, these chiral multiplets, naturally actually lived as coordinates on a Kähler manifold. And that's we saw Kähler geometry appearing. And in this case, we're looking at some particular background that we want to look at. And this is the geometry of the space that we're compactifying on. So I want to try and argue that those two things actually get related to each other. And the way we're going to relate them is we're going to take the 10-dimensional theory and think of it as a 4-dimensional theory. So let's again consider, so let's assume that the 10-dimensional manifold is some product of a 4-dimensional manifold and some internal space, so that we can similarly decompose the spinors into a 4-dimensional part and a 6-dimensional part. So we can think about, so if we have the metric B field phi and A on M6, so if we just restrict, obviously we really have these things on the whole 10-dimensional space. But suppose we only think about the parts of them which are living on the M6 part. So this is a symmetric tensor on here, this is a 2-form on here, and so on. So from the 4D perspective, these are scalars. So what I'm really trying to say is, so for example, if we take the metric, all I'm doing is this, I'm just doing a little bit of decomposition. So I have this is the same as a symmetric product on the 4-dimensional part, something which is a tensor between the 4 and the 6, and then something which is on the internal part. So from a 4D point of view, so 4D perspective, this looks like a metric. This looks like a 1-form with values in T star M6. So it's from a 4-dimensional point of view, it's a 1-form, but it takes values in here. And this looks like a scalar with values in S2 T star M6. So I can do the same decomposition for B, phi, and A, and I just want to focus on the bits that look like scalars. So for each one, I'll get some scalar. But I can also choose some sections. So remember, if here we have a section of this guy is something which looks like a 4-dimensional spinor, tensor, a 6-dimensional spinor. So let's choose some 6-dimensional spinor. But vary the 4-dimensional spinor. So because this guy is fixed now, I'm only allowed to vary this one. There's actually 4 components of that. So effectively now, I only have n equals to 4. Originally, I had n equal to 16 because there were 4 of these and 4 of these. So altogether, I had 16 degrees of freedom. But now I'm fixing this guy. And so when I vary these, I only have 4. So I'm trying to think of the 10-dimensional theory as though it was a 4-dimensional theory. So I'm decomposing everything into sort of 4-dimensional representations. So when you do that, we should have, so again, so the G and the spinor, so G in the 6th-dimensional space in the spinor should again define SU3 structure, right? So I have a metric, so that gives me some, I use that to define what I mean by spin 6, which is SU4. When I fix this guy, I get some SU3. So altogether, so our scalar degrees of freedom, scalars from the point of view of the 4-dimensional part of the space, should be able to package as some SU3 structure, some phi, some B, and some A, where these are all internal. So if I now view the D equals 10, N equals 1 theory as a D equals 4, N equal 1 theory, these scalars, the scalars should become part of some chiral multiplier. Right, remember I told you that the scalar degrees of freedom in the N equal 4, D equals 4, N equal 1 theory were part of a scalar multiplet, so they're part of a chiral multiplet. So in other words, they should be coordinates on some Hodge-Kähler Hodge manifold. What I called Z before. But now this is going to be, but now Z is infinite dimensional. Because these things, omega, except these things are all sections of bundles on M6. So you can think of this in two different ways. If you like, what I could do is take all the internal fields, choose some metric, and decompose into eigenmodes of the metric. Do some Fourier analysis on the internal space. I'll get an infinite number of objects corresponding to the different Fourier modes. But each of those objects will arrange itself as some chiral multiplet of the four-dimensional theory. So it should be that I can reinterpret the 10-dimensional theory as a four-dimensional theory, and then I should get all the structures that I saw from a four-dimensional point of view. So I should get some Kähler-Hodge manifold, I should get some F terms and some D terms. So what we find, so this would imply that the space of objects, these things, should live in some, should have some natural Kähler-Hodge structure. And furthermore, if I now look for a supersymmetric background, well, that's exactly, if you, this background I looked for here, this solution here, was flat Minkowski space. But from the first bit of geometry I did, I know how to understand those backgrounds. They were to do with setting the F terms and the D terms. So furthermore, the supersymmetric background i.e. the whole Strominger system, should correspond to F terms vanishing, F terms, which remember was this thing which was equivalent to some superpotential. So we need some, so there should be some superpotential. And D terms, which correspond to some vanishing of a moment map. So we should have some moment map. So the point is the fact that we can reinterpret the 10-dimensional theory as though it was a four-dimensional theory gives us a new picture of what the supersymmetry conditions should be. They should be formulatable as a set of F terms and D terms. So if you like, this predicts that there should be a moment map for the whole Strominger system. Just because if you reformulate it this way, it sort of has to be. So we're left with some questions. So what is the Kähler metric on Z? How can we go from this set of objects to actually writing down some Kähler metric? And then what are the F terms? Sorry, I'm just saying what I said before. So what is the superpotential? And finally, what group G is giving the moment map? So what I'm trying to say is that by thinking about it this way, you should naturally get some picture of an infinite dimensional moment map, which is just the kind of picture that, you know, appears when you think about Hermitian-Young-Mills equations, or doing Kähler-Einstein backgrounds and so on, or even Calabi-Yau backgrounds. Does this way of connecting them make sense?
Yes, absolutely. Yeah, no, that's very interesting. And I mean, so what you're saying is we should expect, I mean, I'm aware of some moment map formulations for like the Calabi-Yau theory, and this should somehow generalize this.
This should generalize. So I mean, Mario's written down moment maps for exactly this system. We followed through this. So what I would describe maybe next time is to tell you in detail how you get this moment map and what it looks like. Mm-hmm. But you can do it for other cases. So, well, let me just, maybe this is a point to sort of start stopping.
Yeah.
That I can tell you more details. So to see this structure, so what happens is that to see this structure, you need generalized geometry. So the point is that you need to, I mean, this collection of objects looks a little bizarre, right? But it turns out you can repackage them in a way using generalized geometry. So I can summarize, and then I can or cannot give you more information next time. So what happens is that, so for the whole Strominger system, it turns out that there's underlying it, there's some transitive Courant algebroid. So that's some generalized tangent space, which is sort of looks like vectors plus one forms plus some adjoint bundle. And on here, well, this has a sort of natural, so remember this is 6-dimensional. This has a sort of natural SO6 plus the dimension of the group. And then the way I think about it, it's also got some rescaling R plus, but whatever, there's some group sitting there. And all these objects, this omega B phi A, these define a SU3 times SO6 plus the dimension of G structure, which you can think of as this bundle, the complexification of this bundle decomposing into 3 bits. So I know I'm going very fast, but this is the idea. So this is some 3-dimensional part, this is some 3-dimensional part, this is some 6 plus dim G dimensional part. And this, you get a natural Kähler metric on here that comes from it's inherited just from these structures. And then the F terms just correspond to involutivity of, so if I take L minus 1, L minus 1, it has to live in L minus 1, just like an ordinary complex structure. This is under the Dorfman bracket. And then the moment map. So the group is what sometimes gets called the generalized diffeomorphism group, which is just generated by the Dorfman bracket. So it's really diffeomorphisms plus gauge transformations of B. So it turns out there's a sort of gauge transformation of B that goes on. So all the objects here are completely natural from the point of view of the generalized geometry. So the Kähler metric you get comes from thinking about it as a generalized geometrical structure. The F terms just correspond to some involutivity conditions, and they're holomorphic with respect to this. And the moment map is for the obvious group that was sitting there, which is just the set of symmetries of the supergravity, which is diffeomorphisms plus these gauge transformations. So you can show that you can, defining each of these objects, you exactly reproduce the equations of the, setting the F terms to 0, the moment map to 0 just exactly reproduces the equations of the Hull-Strominger system.
I guess I would have expected maybe not to see like the whole generalized diffeomorphism group, but some, I mean, like in the Kähler setting, you somehow get it by looking at diffeomorphisms which fix the Kähler form,
so
or something like that.
Excellent. So this is something that's bothered me when we wrote the paper. And I think the answer is, I was trying to think about it before I gave this talk. I think the answer is the following. So something interesting happens here, which is that the Kähler metric you get is not positive definite. It's got a.
You mean like the infinite dimensional one?
The infinite dimensional one.
Yeah. Okay. Yeah.
It has a mixed signature. And although these F terms are some holomorphic conditions, so they take out some holomorphic slice, if the Kähler metric is indefinite, a holomorphic subspace doesn't have to have, the symplectic form can be degenerate on it.
Okay. Yeah.
And if you work out the symplectic form on this space, it is indeed degenerate. And when you think about the, so what that means is that in the moment map, another way of saying it is that apparently different actions of the generalized diffeomorphisms give you the same moment map if you naively calculate. So the moment map, before you impose the F terms, the moment map's perfectly well defined. The symplectic structure is good. If you impose the F terms, you get to something where it's no longer properly symplectic. It's degenerate. The moment maps that you originally defined before you impose this F term, on the subspace, some of the values of the moment maps for different diffeomorphisms agree with each other. When you take the quotient by the full generalized diffeomorphism group, it does two things. Part of the group, it doesn't complexify properly. When you try and, if you think about it as a complex action, it complexifies into itself. And what it's doing is actually, because the final answer has to give a nice Kähler space, it has to, there's just from supersymmetry. So what happens is the action of the generalized diffeomorphisms do two bits. Part of the generalized diffeomorphisms correct the fact that you had a degenerate Kähler form. So it quotients out the degenerate directions so that you get some non-degenerate Kähler form. And then on that, you're left with a final moment map. So although I don't know the details, my guess is that of the generalized diffeomorphisms, a large part of it deal with the degeneracy of the symplectic form. And then what's left over is something like the symplectomorphisms.
I see. I see. Okay.
One thing you can do is if you take this moment map and you just choose to restrict to symplectomorphisms, do something simple. Take this moment map, set H to 0, just restrict to symplectomorphisms, and the moment map becomes the curvature, just as it should for a Kähler-Einstein space.
Okay.
So it's certainly got that in it. Yeah.
Interesting. Interesting. Okay, yeah, thank you.
So maybe I'll just finish by saying, again, this is just one example. So you can do, so if you change, so you know, if you this same picture can be used for lots of different geometries. So another example, so just as an example, if you take d equals 11, n equal 1, and you go down to d equals 4, n equal 1, this generalizes G2. And what it does is that you now basically, the objects that you had here, this, this structure plus these things, what you get here is you get some, this is some G2 structure, some 3 form, and you get some other 3 form, which comes from the supergravity, and you get a moment map. So by extending this problem about G2s to include all the fields of the supergravity, things get complexified. You get a Kähler manifold of structures, and you get a moment map. So we've now got a moment map for some extension of G2 manifolds. And roughly speaking, what happens here is that the F terms tell you that if you set this extra bit to 0, the F terms tell you that d phi is 0. And the D terms, the moment map terms, tell you that d star phi is 0. So there's some ideas out there that for G2 manifolds, that if you have some closed 3 forms, whether then like there's some notion of then you can always find the corresponding co-closed ones. So this would give you some notion of stability. You look at the space of closed forms, and then if you can argue that it's stable, then there would be some solution to that. So,
and is it right that the sort of, I mean, when I look at that, is it right then that the sort of equations of motions, even for this generalized G2, is sort of classical? It just gives you like a regular G2 structure?
Yeah, so not quite. So, okay, there's a, no, that's excellent. So actually what you get is that, so no, this is the special case where I just choose A to be 0. So more generally, actually, this thing's actually not always, I shouldn't really say this is a G2 structure, actually. It's actually more generally, it gets a bit complicated. This is generally actually some SU3 structure in some complicated way. However, if the manifold is compact, we know that there are no solutions where A is non-zero. Okay. So actually, that tells you something about the obstruction, about the stability. So you can certainly satisfy the F terms with A non-zero, but almost all the ones which have A non-zero must be unstable in this picture. So the only ones that are stable are going to be the ones that are honest G2s, if it's a compact manifold. That's one of these. So there are a set of no-go theorems in that just using the equations of motion of the supergravity, you can argue that certain solutions can't exist, and roughly you can't have a lot of these solutions with these fluxes turned on are forced to, the fluxes are forced to vanish on compact spaces. So that was just some word, but
I mean, it's, you're talking about it like a bug, but it sounds more like a feature to me.
No,
I mean,
it's great.
maybe I misunderstood. I mean, I guess I understand there's some kind of generalization of G2, and then you should have a moment map picture for this PDE, but then in the end, the solutions are actually classical.
Actually G2s. Yeah.
Yeah, that seems like a feature to me. I mean, because I don't think there are, I mean, for these other formulations of G2, I mean, I don't think, well, I guess there are some that have some like variational formulation, I guess.
Yeah, so
natural, but...
yeah, so again, I can talk more about it if you want, but what you have to do this in this 11-dimensional example, and that means you don't actually think about generalized geometry, you think about this exceptional version of it. So you have to look at some generalized tangent space which looks like this. Okay, looks horrible, but it's got lots of forms in it. 2 forms, 5 forms, and some funny object that's a 1-form tensor, a top form. And this has an action of E7 on it, the split form of E7. But you can do it all. It all works out. There's there's an analog of the Dorfman derivative and so on. And yeah, and again, you complexify this bundle. It has some involutive. It decomposes. This structure gives some decomposition. And the F terms are equivalent to the involutivity of one of these subbundles. And then there's a corresponding moment map. Yeah, but no, it is. You're absolutely right. It's a feature. I mean, for the physicists, it was a problem because people wanted to go away from G2s by turning on fluxes. But from this point of view, it's exactly a feature. Yeah. So my instinct is to phrase it as a problem. But no.
Interesting. Yeah.
There are again issues that this thing has the metric on the Kähler space is not positive definite, but you can, I think, well, in the paper we talk a bit about it. You can do the moment map in stages. So there's a normal subgroup which is to do with some of the gauge transformations, and so you can do that bit first, and that seems to get around the problem. Maybe I should stop that.
Sure. Yes. Yeah. Let's thank Daniel. That was great. Yeah.
All right.
Thank you. Thank you.
So I could